Alright guys, so this is take 2 on trying to do these notes. Alright, so 9.3 Taylor's theorem. You can tell that I've kind of changed the notes a little bit. I took the combo notes and what it was trying to say, and I found something that's a little bit more streamlined. So we're going to use this. I did put the new form up on iLearn, and it does say the new. The examples are still the same, but you know, I did take out a lot, and you'll notice, and I did add some examples. So what Taylor's theorem basically is the Lagrange form of the remainder. It's also called the Lagrange error bound or Taylor's theorem remainder. So basically, in our notes, and I'll show you guys in a minute kind of why I took it out. But here's the idea. Suppose we didn't have a calculator, but we were interested in the value of sine of 1. So how could we approximate its value? Now, when we say approximate, we kind of are doing just that. We're approximating. We're not getting an exact value without a calculator. So there's a few things. You can either eyeball the graph, be like, okay, here's my sine function, here's 1. We've got our pi over 2 right here, so maybe there's 1 right there. We can compare it to something that is close, which is sine of pi over 3. We know that is square root of 3 over 2, so we can approximate what 1 is. But what we have been doing right now is using Taylor series, right, or Taylor polynomials. And if you remember, the reason why I'm putting this with it is the tangent line approximation is a Taylor series polynomial just to the second degree. So if we did choose the third or fifth option, which are both Taylor polynomials, because they are easy to evaluate, is there a way, depending on the degree of the polynomial we decide to use, to determine how accurate our approximation is? So how far off? That is, do we know what remains from our approximation to get an actual value? And that's the idea. Okay, so we're going to be approximating, but we want to figure out how far off was our approximation. What is our error bound? Okay, so when a Taylor polynomial, Tn of x, centered at x equals c, is used to approximate a function f of x at a value x equals a near the center, but not at the center, we can express our result as follows. Okay, so if the function is equal, okay, remember usually what do? We use approximation sign, but if the function is equal to the polynomial approximation plus the remainder. So if we can figure out the remainder, then we can change our little squiggle into an equal sign. So if we can figure out the remainder by using this idea right here, then we know that the remainder is equal to what the function is minus the polynomial approximation. So here's the idea. The blue graph right here, you can see it as f of x. Okay, we approximate with this polynomial, with this Taylor polynomial right here, centered at x equals c. So we know that at x equals c, the interval, that the two function and the polynomial converge perfectly. But what if we wanted to know a value close to c, but it's not at c? So let's say x equals a. So that means between our actual function and our Taylor polynomial, there's a little error. Okay, there's the error. So this is not an approximation, it's an actual answer because they cross perfectly. But any value to the left or to the right of the centered value, so let's say a or negative a, okay, is going to be an approximation. So what the Lagrange, whatever you want to call it, does for us is it helps us to determine what the value is at x equals a and what is the maximum error, okay, that that I'm going to have if I move left and right on this graph. So written mathematically, what this is saying is that if the function is equal to the Taylor, you notice now how we are saying equal, to the Taylor polynomial plus the remainder at this value a, then I can say that the remainder is equal to the function minus our polynomial function, aka our Taylor polynomial. So it's defined as Rn of a to be the absolute value of the Taylor polynomial at a minus f of a. And that means that basically that the remainder must be less than or equal to, okay, you have to change that if you download this these notes, must be less than or equal to the derivative n plus 1, so depending on which degree we're dealing with, of a point z, the absolute value of that, over n plus 1 factorial times a minus c n plus 1. And basically a minus c, if we're using a Maclaurin, okay, if it's a Maclaurin series, we know that c is going to be 0. But if it's a Taylor centered someplace else, then of course then we'd have to identify that. And then a is where we would like to approximate our graph. So the idea is that what does this mean? This right here, saying that the derivative n plus 1, so fourth derivative, fifth derivative, whatever it be, of some point z has to be less than or equal to the maximum value on this interval c to a. So basically it's the maximum error from here to here. What is the max error I can have? Okay, and we'll look at that once we get there. Okay, so really quick, in the notes, okay, to sum everything up, the Lagrange form of the remainder, if we use this remainder to help us determine error bounds, then refer to those bounds as Lagrange error bounds. This theorem on its own isn't very useful, but what is useful is to be able to calculate the bound for the maximum error on the interval. This leads us to a remainder estimation theorem, which is what we were just talking about right here. So the max error has to be less than, and you notice why I kind of changed it is because this is exactly what we were saying, it just looks a little bit different, okay? So the idea is that m is the max value of the derivative on its domain when r equals 1. And we'll come back to that in an example and it will explain what that is saying. Okay? So, to sum it all up, here's Taylor's theorem. If a function f is differentiable through order n plus 1 in an interval containing the center x equals c, then for each x equals a in the interval, there exists a number, z, between a and c that fits this. So basically the function is going to be f of c, right? Where is it centered? Plus f prime of c, a minus c, f double prime of c. This is just the Taylor polynomial. The difference is that by changing this to an equal sign, we have to add this part right here at the end. We have to add that remainder, where the remainder is given by this right here. You don't really need these absolute values on the outside. Okay, and this is called the Lagrange remainder. So when applying Taylor's formula, Oh, and again, this has to be less than or equal to. Sorry about that. Okay. When applying Taylor's formula, we would not expect to be able to find the exact value of z. Rather, we are merely interested in the safe upper bound, the maximum value for this. So we're not going to find the exact value if you input z. We just want to find the safest max value, from which we will be able to tell how large the remainder is. So let's start. Let's use the fifth degree Maclaurin polynomial to approximate the sign of 0.4. Okay? So fifth degree Maclaurin polynomial. So that means we want to go all the way to n equals 5. So if you remember that the Maclaurin polynomial for sine of x is approximately x minus, right? It's the odd numbers, x cubed over 3 cubed, plus x to the 5th over 5 cubed. So we're going to stop here because we got to n equals 5. So now we can just plug this in. So it's sine of 0.4 is approximately, right? We are approximating, so we're putting the approximation sign. 0.4 minus 0.4 cubed over 3 factorial plus 0.4 to the 5th over 5 factorial. Plug that into the calculator, you get about 0.39. So we approximated sine of 0.4 using the fifth degree Maclaurin polynomial. Okay, and remember Maclaurin means that it was centered at 0. Our x was 0. So example 2 follows this exact same thing. Use the fifth degree Maclaurin polynomial approximation from example 1 to determine the accuracy of the approximation. In other words, what is the exact value of sine of 0.4? Which means, let's use the tool that we have, which is our calculator for now. So the exact value is 0.38941834423. Okay, that's the number I get in the calculator. So how does the Maclaurin approximation compare with the sine of 0.4? It's actually pretty good. It's excellent. Alright, how big was our error? We're going to basically use this formula right here to figure out what our error was. And our remainder, or our error, was what is our t fifth of 0.4, so our Taylor polynomial, or we can call it the Maclaurin polynomial, minus f of 0.4 absolute value. So what did we get from our first answer? From our Taylor polynomial was 0.39. From our actual function we got 0.38941834432. Subtract that, you get 0.000581. So that is our remainder, aka our error. So the idea is that my approximation of 0.4 is that if I take my 0.39 and I subtract or add that remainder, that will put me in my in the place I want to be to get a exact approximation. Alright, let's do another example. So this says determine the degree this says determine the degree of the Maclaurin polynomial that should be used to approximate the cube root of e to 4 decimal places. So recall that the cube root of e is the same thing as saying e to the 1/3. So we're going to basically use the function f of x equals e to the x to evaluate the Maclaurin polynomial at x equals 1/3. Alright, so basically the idea is that we're going to use f of x equals e to the x, which we know that the Maclaurin polynomial of this is 1 plus x squared over 2 prime plus x cubed over 3 prime plus x fourth over 4 prime, and so on and so on. Okay, but now we're going to use this to find the Maclaurin polynomial at x equals 1/3. So that means our sorry, 1 second. So I'm trying to figure out which degree, so how far do they want us to go? In this problem. So let's look. So we got e to the 1/3 when n equals 0. That's going to be 1, right? Now the e to the 1/3 when n equals 1 is going to be 1 plus our 1/3, right? You plug that into your x, which is 1.333 repeating. When n equals 2 of e to the 1/3, it's going to be 1 plus 1/3 plus 1/3 squared over 2 factorial, and that gives us approximately 1.38888 repeating. When n equals 3, it's going to be e to the 1/3 equals 1 plus 1/3, 1/3 plus 1/3 squared over 2 factorial plus 1/3 cubed over 3 factorial. And that gives us approximately 1.39506. Keep going to n equals 4, and this is going to be e to the 1/3, which gives us an approximation. If I just plug that in and then one more term, you get 1.39558. Keep going, n equals 5, e to the 1/3. Plug that in, you get 1.39561. So the idea is, what are they asking? Okay, so the idea is determine the degree. So we want to figure out how far out are we going to go of the Maclaurin polynomial that should be used to approximate this to 4 decimal places. Okay, so our answer is going to be e to the 1/3 is going to be the best approximation at what degree? At n equals what degree? That's what we're trying to figure out. And we're going to be to approximate this to 4 decimal places. Okay, so what that means is that we need to figure out our error as we go. So just going to make a little table. Oops. Okay, and this is going to tell us our error. Okay, so our error to 4 decimal places basically means that we want to get 4 zeros before we get a set number. Okay, I wish I had my calculator, but yeah, I'm going to need my calculator to solve these errors. Alright, I'm going to stop here on this problem because I will need my calculator to calculate the errors to figure out at which degree I need to stop. Okay, when can I stop to get four decimal place approximation? Alright, so we won't be able to answer these two right here. And then if you notice that the next problem is actually very similar, but it asks it a different way. So let's leave example 3, 4, 5, and 6 for part 2. And then we'll do this one together in class. The last example, I know it's called example 5, but it's supposed to be example 7, because this was from the 2011 BC exam. Alright, so we're going to stop here. Good luck. This is, it's not that hard of a section, but it's hard to understand what it is that they're asking you and what to do. But you are going to be doing the same exact thing every single time, so don't freak out. We'll do a lot of examples to make sure that we understand when to use the Lagrange error or Taylor's theorem to figure this out. Okay? Alright, good night.